What if I told you you can take your existing web application and make it more efficient and scalable? It's not possible, you'd cry. Well, you're in for a surprise. Welcome to my talk, Scalable Web Applications. My name is Samuel Williams, and I'm a Ruby Core team member. Today, we are going to talk about scalability and how Ruby 3 unlocks the next evolution of concurrency to help you build scalable web applications. Firstly, let's talk about scalability. From a software perspective, scalability is about how a system's performance changes as the requirements on the system grow. A simple example would be, does your system get slower as the number of users increases? There are lots of different ways to talk about scalability, but let us consider 4 key questions. Can I add capacity to handle increased demand? This is perhaps the biggest problem when building scalable web applications. While trivial applications can be easy to scale up, once you start depending on external services such as databases, key value stores, software as a service, it can be hard to know which parts of your system are causing performance issues and how to mitigate them. In many cases, limited or metered resources are something that needs to be carefully monitored, as they can cause contention. As you try to increase the capacity of one part of your system, you can run into limitations in another part. As an example, if you increase the number of web server instances without considering the limitations in your database, you might exceed your database connection limit, and this will restrict your web server's ability to serve more users, potentially resulting in errors. Another example of metered resources includes third-party software as a service. These hidden scalability issues are often overlooked when developers plan their architecture, and mitigation can be especially difficult because you are depending on someone else to scale with your requirements. Building computationally efficient systems ensures that your applications remain stable and responsive even as the problems they solve grow in size. Choosing the right algorithms and topologies are critical during the early stages of your web application because the wrong decision can be very costly to fix later. As an example, ensuring that your database queries are using indexes correctly can have a big impact on application performance. As your data access patterns change, your indexes may become suboptimal and cause performance regressions. Will my application tolerate transient and enduring faults? As your system grows in use, the impact of a single fault also grows in size. While this may not be immediately obvious, it can have a significant impact on your business and your users. Fault tolerance is the ability of a system to keep functioning even if one part fails. Ideally, systems have enough redundancy to continue working until the fault is resolved. An example of this would be a database cluster with multiple replicas. If one replica fails, the cluster continues to operate at reduced capacity until a new replica can be provisioned. Ideally, your application code should not need to know about the fault. Internally, the request should be rerouted to a working replica. By building isolated systems, faults can be contained. In web servers, this can be achieved by using a multi-process model. If one process crashes, the others keep on working. Another way to achieve this is to move logical units of work into background jobs. This works especially well for external service providers who might encounter transient failures. The background job queue also acts as a load leveling mechanism. This also applies to security. For example, having one system responsible for application logic and another isolated system responsible for sensitive information. Do I understand the health and performance of the live system? Lack of visibility into an application makes it hard for developers to identify and fix problems. Capturing errors, latency, and metrics from a production environment is essential to smooth operations. An analysis of trends can help prevent scalability issues before they occur. Having good tools for logging errors and latency is critical to identifying problems which need to be addressed. Capturing specific traces of an application's execution provide valuable insights into scalability issues. As an example, database logs can help developers find and fix poorly performing queries. Understanding usage patterns and tracking application metrics becomes more important as utilization increases. Aggregations and historical data help you understand trends and changes in application performance. This data can form the basis for alerting developers when something is going wrong and to help identify different parts of the system which are impacting the scalability of an application. Can I build the system with my time and cost budget? As a business seeks to grow and acquire more customers, how their systems are designed will impact their ability to build new features and maintain existing ones. Different programming languages and frameworks have different approaches to scalability, and this can impact developers and their ability to deliver features on time and on budget. Rewriting your web application to improve scalability can be a very difficult process. The alternative approach is known as lighting money on fire, and it is when you simply over-provision everything to the point where you achieve the service level you require. An example of this would be adding excessive amounts of hardware to the database cluster rather than optimizing poorly performing queries. Unfortunately, or maybe fortunately, this approach will only get you so far. It's also important to consider the resource consumption of any given system. Efficient, scalable systems are great for the planet. Less resources are required for the same work. The technology sector is responsible for about 2% of global carbon emissions, and as a civilization, we are facing an unprecedented set of challenges relating to climate change. We can help by improving the scalability of our systems to reduce natural resource consumption and energy utilization. Our systems can also help to build a more efficient society. This is a good thing and something we can take responsibility for. So we have talked about 4 areas which underpin any scalable system: the ability to expand capacity, the ability to isolate faults and problems, visibility into your application behavior and performance, delivering your applications on time and within budget. But how does this apply to Ruby, and how can Ruby facilitate these goals? Ruby is a great language for building web applications. It has a certain simplicity and elegance which is hard to find in other languages. Many success stories support its continued usage, and yet, looking at the latest trends, we see alternative platforms becoming more popular. The stability of Ruby as a language is both its biggest strength and also a significant weakness. Ruby is ripe for innovation, and I'm proud to share with you that Ruby 3 will include a new, lightweight scheduler for improved concurrency. This gives Ruby a transparent, event-driven architecture. Taking advantage of this scheduler enables simpler, robust systems with improved scalability, without requiring significant changes to application code. The initial design was conceived of in 2017, and finally this year, in 2020, we made a formal proposal for Ruby 3. This proposal specifies the scheduler interface, which can work across different interpreters, including CRuby, JRuby, and TruffleRuby. The actual implementation of the scheduler is provided by a separate Ruby gem. The most popular event-driven platform would probably be Node.js. Initially, they used callbacks exclusively to implement continuation passing style concurrency. Callbacks can be hard to reason about because they invert the flow control of your code. Instead of sequential execution, you end up with your program split up into separate callbacks, and the order of operations is often ambiguous. To simplify chaining callbacks together, promises were introduced. A promise can be resolved, and this triggers the attached callbacks. They are semantically identical to continuation passing style callbacks and present all the same problems, although they are slightly easier to use in practice. In order to fix the inversion of flow control, new keywords were introduced to hide the use of promises and callbacks. Many languages have adopted this approach, but the biggest problem is that it requires existing code to be rewritten. This ultimately results in functions which are incompatible with each other, normal functions and asynchronous functions. I wanted to avoid this in Ruby, so about 4 years ago I started experimenting with fiber-based concurrency. Fibers allow you to write asynchronous code without the inversion of flow control that occurs with callbacks. In effect, they present the same sequential execution as async await, but without the extra keywords. Every function is optionally asynchronous, and the fiber itself suspends its execution until the result is ready. Let us compare the performance of Ruby 2.7 and Ruby 3 with the same net HTTP code. Firstly, we are going to use async. We are also going to use async barrier, which allows us to execute multiple tasks and wait for them all to complete. We're also going to depend on net HTTP and URI for parsing. Firstly, let's create a list of topics. Now, we're going to create an asynchronous block. We create a barrier which will help manage the concurrent tasks. We're also going to log the progress of our operations. Now, for each topic, we will create a nested asynchronous task. Then, inside this task, we will perform the net HTTP GET, and we will do a Google search for the given topic. Finally, we don't really care about the response, but we will log the progress. Then, we will wait for all the tasks to complete. So let's execute this with Ruby 2.7. What we see is one request happening after the other. The latency is equal to the sum of all the requests. Now let's try this with Ruby head. What you see is all the requests happening concurrently, and thus the total latency is greatly reduced. In Ruby 2.7, each request consists of two parts: sending the request to the remote server and reading the response when it comes back. In between these two operations, we need to wait for the network, and this time is wasted. When we look at 7 sequential requests, each request happens after the previous one because net HTTP GET is a blocking operation, and it has a very high latency going from my laptop to Google and back again. We must wait for a long time for all the operations to complete. But there is no reason for us to wait like this. In Ruby 3, this operation becomes non-blocking, and we can interleave all 7 requests, which improves the total latency significantly. This is something which you can easily take advantage of in your web application, if you are, for example, accessing external services. We have worked hard to make this compatible with existing code where possible. The only requirement is for you to break your code up into logical blocks that can be run concurrently. However, in many cases, this can be done automatically. Individual web requests are already able to be executed concurrently. The same applies to batch processing systems. By taking advantage of these existing models, we can improve the scalability of Ruby web applications with minimal changes. Let us look at how Ruby 3 enables us to use the existing Redis Gem with minimal changes. Again, we are going to use Async. We create a top-level asynchronous task. And in that, we create a child asynchronous task. We connect to the local Redis instance. In this task, we are going to perform a blocking list pop, which essentially waits for an item to be put into a list and then returns it. Then we're going to print it out. Now we connect to Redis in the top level task, and we are going to put an item into that list. Then we wait for the child to finish. Okay, let's try this with Ruby 2.7. What you notice is that this program hangs because it's waiting for an item to go in the list, and this is a blocking operation. The parent task never gets a chance to add the item. Using Ruby 3, the Redis operation becomes non-blocking, and both tasks get a chance to execute. In Ruby 2.7, because the Redis BL pop is a blocking operation, the parent task never gets a chance to add the item to the list, so the program hangs forever. However, taking advantage of the scheduler in Ruby 3, this operation becomes non-blocking. So while we are waiting to pop an item off the list from one task, we can use another task to push the item. This kind of concurrency enables new ways of building scalable systems. So we have used a gem called Async several times now, but what does it do and why is it important? Async provides the scaffolding for building reliable, scalable applications. It implements the event loop, which is used for scheduling the non-blocking operations, and it can transparently take advantage of the new Ruby 3 scheduler interface. As we have seen, Async provides a structure for executing your programs concurrently. Within those tasks, your code executes sequentially. No special keywords or changes to program logic is required. Lately, I've been looking into Async as one of my projects would really benefit from non-blocking I/O. It's really beautifully designed. Janko Moronic on the general design of Async. The next most critical component for building scalable web applications is the web server. FALCON is an async-based web server which helps you build highly scalable web applications. It executes each request in an asynchronous task and transparently handles non-blocking operations. FALCON is implemented in pure Ruby, yet in performance it rivals other servers which have native components. Because of this, it is very easy to use, deploy, and customize. Out of the box, it supports HTTP 1 and HTTP 2 with zero configuration. This provides a modern development and production platform for Ruby web applications. Is it scalable? Well, like anything, it depends on how you use it. But various micro benchmarks show that it can perform very well, especially when there are operations which are non-blocking. This graph shows Puma versus FALCON. Puma plateaus at 16 workers, while FALCON is able to scale up until all CPU cores are pegged. We also recently demonstrated 1 million WebSocket connections to a single FALCON instance. Async is the right model because web apps are almost always I/O bound. The Ruby web ecosystem is really lacking in scalability, for example WebSockets on Puma. Async unlocks the next tier of scalability in the most Ruby-like way possible. Brian Powell on migrating from Puma to FALCON. Does it work with Rails? Yes, it's rack compatible. And with the additions of the new Ruby 3 scheduler, it can transparently improve the scalability of your existing applications. Accessing data is a critical part of most web applications. Active Record is a commonly used gem for accessing databases. It currently uses one connection per thread. Because of that, multiple independent fibers on the same thread may be held up waiting for the connection. This is a design choice that limits concurrency. Fortunately, there is discussion happening right now about how we can improve the situation. Not all databases use non-blocking I/O. However, this can be addressed. The maintainer of the Postgres gem is interested to add support for non-blocking I/O. I believe we will see expanded support from other maintainers once Ruby 3 is released. As an alternative, we recently started implementing a low-level database gem called DB. It provides non-blocking Postgres and MariaDB access. You can use this today if you want low-latency streaming database queries. Redis is a commonly used system for key-value storage and in-memory data structures. As we have demonstrated, the Redis Gem is compatible with the Ruby 3 scheduler with no changes to application code required. However, we also have our own implementation called Async Redis, which was built from the ground up for concurrency and has more convenient connection pooling built in. HTTP is a key protocol of the modern web. There are many clients, and they should all be compatible with the Ruby 3 scheduler. In order to support all the features we wanted for FALCON, we built our own Async HTTP. It provides client and server support for HTTP 1, 2, and hopefully soon 3. Along with this, we also have Async WebSocket, which supports WebSockets over HTTP 1 and 2. This makes it trivial to build scalable web applications with shared client and server state. Let's take a look at a web application which is running on FALCON and uses some of the technology we have talked about. This web application implements a multi-user chat room. It's built using a web framework called Utopia. Let's look first at the view layer. The page is very simple. It has an output area for logging the chat messages and an input text field. This interface is driven by JavaScript. Let's take a look at that now. The JavaScript consists of two main parts. After connecting to the server using an HTTP2 WebSocket, it waits for the user to type a message. When the user presses the Enter key, the message is sent over the WebSocket. The other part is simply waiting for the messages to come from the WebSocket. When the message is received, it is appended to the chat output. On the server side, we have a fairly standard controller method. This method creates a special rack response which embeds a WebSocket connection. On the server, for each connection, we connect to the local Redis instance. We subscribe to the channel chat general and wait for incoming messages. When a message is received, it is written out to the client through the connected WebSocket. The other important part is receiving WebSocket messages. When a message is received, it is published to the Redis instance. By doing it this way, all messages go via Redis, and all connected clients receive those messages. Here I have FALCON running 8 processes. It is running the application we just looked at. Here I have 2 Chrome windows, each attached to a different process ID. Over here, I have a terminal showing the output of the chat general pub/sub queue in Redis. If we type a message into the client, we see it goes through Redis and comes out on both clients. How does it perform? We are comfortable recommending around 5,000 active WebSockets per process. More than this, and the Ruby garbage collector overhead can become an issue. As we push the limits of Ruby beyond what anyone has done before, we find more areas that require attention, and we look forward to tackling this problem in the future. We also have extensive benchmarks which compare FALCON, Puma, Unicorn, Passenger and Nginx in different situations. FALCON is consistently on top, especially when it comes to non-blocking workloads. So, what are the next steps? It depends on you. The community. Please try out these new features in Ruby 3 and give me feedback. And the businesses. I hope these new ideas can provide opportunities for innovation. Please support this important work. Thank you for listening to my talk.